Welcome to our lesson on Cramer's rule for solving systems of linear equations in three variables. Cramer's rule provides a systematic method to find the values of unknowns using determinants, which can be particularly useful for 3x3 systems. Let's start by understanding what a system of linear equations in three variables looks like. Consider a general system with unknowns x, y, and z. Each equation is a linear combination of these variables equal to a constant. Here, a, b, and c represent the coefficients of x, y, and z respectively, while d represents the constants on the right side. Now, to apply Cramer's rule, we first need to form the coefficient matrix. This matrix, A, contains all the coefficients of our variables. The first column contains the coefficients of x, the second column contains the coefficients of y, and the third column contains the coefficients of z. Next, we need to calculate the determinant of this coefficient matrix. Let's denote this determinant as capital D. The determinant of a 3x3 matrix can be calculated using various methods, such as the rule of Serres or cofactor expansion. One way to calculate the determinant is using the cofactor expansion formula, which looks like this. This formula involves the products of elements from different rows and columns. It might look complicated, but we'll work through an example to make it clearer. Before we proceed, it's important to note that Cramer's rule works only when the determinant of the coefficient matrix is not equal to 0. If D equals 0, the system either has infinitely many solutions or no solution at all. Now, assuming D is not 0, we need to form three additional matrices: A underscore x, A underscore y, and A underscore z. To form A underscore x, we replace the first column of matrix A, the x coefficients, with the constants d underscore 1, d underscore 2, and d underscore 3. For A underscore y, we replace the second column, the y coefficients, and for A underscore z, we replace the third column, the z coefficients. We then calculate the determinants of these three matrices. Let's denote them as d underscore x, d underscore y, and d underscore z, respectively. These determinants are calculated using the same formula as we used for D. Finally, we apply Cramer's rule to find the values of our unknowns. The value of x is d underscore x divided by d. The value of y is d underscore y divided by d. And the value of z is d underscore z divided by d. This gives us the unique solution to our system of equations. Let's now work through a numerical example to solidify our understanding of Cramer's rule. Consider the following system of equations. Step 1. Let's identify our coefficient matrix A. This matrix contains the coefficients of x, y, and z from our system. The first column has the coefficients of x, 2, 1, and 3. The second column has the coefficients of y, -1, 4, and 2. The third column has the coefficients of z, 3, -2, and 1. Step 2. Let's calculate the determinant of matrix A. We'll use the cofactor expansion formula. Let's break it down step by step. Using the cofactor expansion formula, we have D equals 2 times the determinant of the submatrix formed by removing the first row and first column, minus -1 times the determinant of the submatrix formed by removing the first row and second column, plus 3 times the determinant of the submatrix formed by removing the first row and third column. Let's calculate each of these 2x2 determinants. For a 2x2 matrix, the determinant is the product of the diagonal elements minus the product of the off-diagonal elements. Applying this to our submatrices, the first submatrix gives us 4 times 1 minus -2 times 2, which equals 4 plus 4, which is 8. The second submatrix gives us 1 times 1 minus -2 times 3, which equals 1 plus 6, which is 7. The third submatrix gives us 1 times 2 minus 4 times 3, which equals 2 minus 12, which is -10. Now we can calculate the determinant D. D equals 2 times 8 minus -1 times 7 plus 3 times -10, which equals 16 plus 7 minus 30, which is -7. Since D is not 0, we can proceed with Cramer's rule. Step 3. Let's form matrix A underscore x by replacing the first column of matrix A with the constants 7, -1, and 12. We calculate the determinant of A underscore x using the same method. D underscore x equals 7 times the determinant of the submatrix formed by removing the first row and first column, minus -1 times the determinant of the submatrix formed by removing the first row and second column, plus 3 times the determinant of the submatrix formed by removing the first row and third column. Calculating each of the submatrices, The first submatrix gives us 4 times 1 minus negative 2 times 2, which equals 4 plus 4, which is 8. The second submatrix gives us negative 1 times 1 minus negative 2 times 12, which equals negative 1 plus 24, which is 23. The third submatrix gives us negative 1 times 2 minus 4 times 12, which equals negative 2 minus 48, which is negative 50. Now we can calculate the determinant d underscore x. D underscore x equals 7 times 8 minus negative 1 times 23 plus 3 times negative 50, which equals 56 minus negative 23 minus 150, which is negative 117. Let me double check that calculation. D underscore x equals 7 times 8 minus negative 1 times 23 plus 3 times negative 50. That's 56 plus 23 minus 150. Which is 79 minus 150, which equals negative 71. Similarly, we can calculate d underscore y and d underscore z. I'll speed up this process since we've already seen the method in detail. For matrix a underscore y, we replace the second column with the constants 7, minus 1, and 12, calculating the determinant of a underscore y using the same method. D underscore y equals 2 times negative 1 times 1 minus negative 2 times 12 minus 7 times 1 times 1 minus 3 times negative 2 plus 3 times 1 times 12 minus 3 times negative 1. This simplifies to 2 times 23 minus 7 times 7 plus 3 times 15, which equals 46 minus 49 plus 45, which is 42. For matrix a underscore z, we replace the third column with the constants 7, minus 1, and 12. Calculating the determinant of a underscore z. D underscore z equals 2 times 4 times 12 minus 2 times negative 1 minus negative 1 times 12 minus 3 times negative 1 plus 7 times 1 times 2 minus 3 times 4. This simplifies to 2 times 50 minus negative 1 times 15 plus 7 times negative 10, which equals 100 plus 15 minus 70, which is 45. Step 4. Now we can apply Cramer's rule to find the values of x, y, and z. X equals d underscore x divided by d, which is negative 71 divided by negative 7, which equals 71 divided by 7, approximately 10.14. Y equals d underscore y divided by d, which is 42 divided by negative 7, which equals negative 6. Z equals d underscore z divided by d, which is 45 divided by negative 7, which equals negative 45 divided by 7, approximately negative 6.43. Let's verify our solution by substituting these values back into our original system of equations. For the first equation, 2 times 10.14 minus negative 6 plus 3 times negative 6.43 equals 20.28 plus 6 minus 19.29, which is approximately 7, matching our right-hand side. You can verify the other equations similarly. This confirms that our solution is correct. To summarize, Cramer's rule provides a systematic method for solving systems of linear equations using determinants. The key steps are: 1. Form the coefficient matrix A and calculate its determinant D. 2. Form matrices A underscore x, A underscore y, and A underscore z by replacing the corresponding columns with the constants. 3. Calculate the determinants d underscore x, d underscore y, and d underscore z. 4. Find the values of the unknowns using the formulas x equals d underscore x divided by d, y equals d underscore y divided by d, and z equals d underscore z divided by d. Remember, Cramer's rule only works when the determinant of the coefficient matrix is not 0. While Cramer's rule is elegant and straightforward for small systems, it becomes computationally intensive for larger systems due to the increasing complexity of determinant calculations. However, for 2x2 and 3x3 systems, it remains a useful and efficient method. Thank you for watching, and I hope this has helped you understand how to apply Cramer's rule to solve systems of linear equations.